when something is spinning in a circular pattern there, like a wheel, that wheel has what we call rotational kinetic energy. It doesn't matter if it's the wheel, like a bicycle wheel on the ground is moving or just spinning it. You're holding the bicycle wheel up in there, you're spinning that. That wheel has a lot of kinetic energy, because if you take a string attached to it and attach it to a little bucket in the bottom, probably will raise that bucket up there. Why did the bucket move up there? Because of the kinetic energy in that wheel there. So if you remember kinetic energy, the definition of kinetic energy is what? 1/2 mv squared, right? And if you recall from last class, V equals what? R times W. So if I come back and plug it in place of V, let me put R times W, and let me square it. This becomes 1/2 m R squared W squared. Now, let me take mr squared and group them together. Now we have a new term here. It's called inertia. Inertia is equal to the summation of mr squared. We use the letter I for that. So then you can take this equation, K, and write that 1/2 I W squared. So for example, let's talk about inertia here. Let's say I have a string, not a string, let's say a rod, really light rod, has no mass. Neglect the mass of the rod. And I take a 5 gram and attach it at the 0 mark here. And I take at 20 grams here and attach it at the 30 centimeter mark. And I start spinning this at right there. This is the 20 centimeters. And I start spinning that rod at the 20 centimeters, spinning it like there's a pivot point here, and this is spinning. Then this will have an inertia, I, is equal to the summation of all these masses times r squared. So the inertia for that will be the mass of this. What's the mass of this? That's 5 grams, or 0.005. And what is the distance from here to there? From here to there?
20 centimeters. So
that's 0.2 squared. 20 centimeters, 0.2 meters, plus the mass of the 20 gram, which is 0.020, and times the distance from here to there. That's the radius from the pivot point to that spot there. And what's the distance from here to here?
10 centimeters.
10 centimeters. And that becomes the inertia. If I neglect the mass of that rod there, if it's not there, that's the inertia for the system. I got everything in front of me. Oh, no, I did get it. I thought I forgot my calculator. It's right here. 0.005 times 0.2 squared plus 0.020 times 0.1 squared. And I came up with the inertia being 0.0004. What do you think the units for inertia is? What is the unit for the mass?
Grams.
Kilograms.
Kilograms.
And what is the unit for the radius? Meter. So kilogram meter squared. So So the unit for the inertia is going to be this. The value is 0.0004 kilogram meter squared. Do you have a different answer? You guys got?
Yeah, but her
I just
calculator's
skipped,
weird.
and I just think I skipped a step.
Yep. I could be wrong. I'm horrible with calculators.
No,
Oh,
you're,
no,
Yeah.
no, you're right.
Calculator
Yep.
broke last night.
4 times 10 to the negative fourth is the same thing, right?
Correct.
Okay.
So this is 4 times 10 to the negative 4. The question is, when we start doing these problems, how are we going to calculate the inertia? Especially when you get a wheel or a disc. That becomes more challenging. But that's the equation for rotational kinetic energy. I'm going to use R for rotation when things are spinning. So the kinetic energy due to rotation, it's 1/2 the inertia times W squared. So, but what happens if this rod is not, you can't neglect the mass of it? Then you got to take the center of this rod, which is the 15 centimeter, and pretend there's a weight straight down right there at that spot, and use that. What about if it's a wheel? What about if it's a solid disc? You got to cut it into little pieces. Well, we're not going to do that. The book says, you know what? We're going to make life easy on you. We're going to give you the inertia for the most common shapes you're going to be using. And here's a table in our book. Can you see it? Right there. These are the inertias for every shape we're going to be using. If it is a hoop, like this one, a ring, just an outside ring, the inertia I equals mr squared. If it's a solid disk, the inertia is 1/2 mr squared. It's spinning around the center. If it's a solid disk spinning around the edge, the outside edge, it's different. It is 3/2 mr squared. If it's a ruler like this, spinning around the center of it, it is 1/12 m times the length of that squared. If it's a ruler spinning on the edge of it like this, this is 1/3 ml squared. If it's a sphere, hollow sphere, solid sphere is like a basketball spinning around the edge of it instead of the center. We have different equations for each one. So we're going to be using that chart to calculate what the inertia is. We can't calculate the inertia for them straightforward because it's the summation of mass times r squared. The only one to do that is to cut this. When you have one like this, if you really want to go and calculate the inertia, or if you have a solid disk like this, how do you find the inertia for that? You got to break it into little tiny pieces like these, the square here, and go how far this from here. And just, if I have that shape, I got to visualize it like this. And none of us going to do it that way. You say you're going to spin around the center. This is a solid disk. I got to picture this as little tiny pieces like this next to each other. Stacked, you know? So you got to find each piece. What's the mass of it times the radius? mr squared. Grab the next piece, m times r squared. Grab this one, m times r squared. Every one of them and add them. Yeah, good luck. So we will not be doing that. We'll be using that chart. So let's see how we're going to deal with these. Let's take a few examples. So we have this beam, a rod, could be a ruler here. Let's give it a mass. Somebody pick a number for it. What do you want to use for the mass of it? 1 kilogram? Okay. And you're going to spin this around the center or the edge of it. Let's say this is a prop, like a blade for the lawnmower. So 1 kilogram, probably reasonable, probably even more than 1 kilogram, and spins around the center. How long the blade? Usually what, 22 inches? I think 21, 22 inches lawnmowers. So what is 20? What is my ruler here? 22 inches. The radius would be what? Roughly 10 inches. Let's say R equals 25 centimeters. That's from here to, or the length of that, the length will be, well, instead of R, the length of this, 50 centimeter. I'll go like this. $25 from here, that's what I meant, from the center to that, if you split, it's not a circle yet. So that's a blade for the lawnmower. You turn the lawnmower on, the thing starts spinning. And I have no idea what the RPM on the lawnmower is. Anyone? Any clue? Jason, you seem to know the stuff last time about cars. What about lawnmowers? Do you know what the RPM on them?
No.
50.
I think it's more than 50 revolution per minute. Let's say 200. I have no idea.
Yeah, I don't know that much, and I don't think I would
Yep.
publicly state as much.
Let's say 200 RPM, just for the sake of discussion. How much rotational kinetic energy does that rod has in it? Well, first I need to know what W is. Remember, I'm leaving a space for a reason here. So I'm leaving a space on top of the paper. The kinetic energy due to rotation. The lawnmower is sitting on the ground, spinning. The blade is spinning. It has kinetic energy. You want to know how much kinetic energy it has? Stick your finger under it and see what will happen. That's how much damage will do, that energy there. Or try to stop it. Put a rock there and try to stop it and see what will happen. So the kinetic energy due to rotation, it says 1/2 I W squared. So I need to know what I is, I need to know what W is. So what is W? First thing first, let's find W. Well, we know that it's 200 RPM or revolution. That's RPM per minute, right? Let's change it to rad per second. Revolution, rad. 1 rev is equal to 2 pi. So my answer now in rad per minute. I don't want per minute, I want it per second. Minutes on the bottom. I want minutes on the top, seconds on the bottom. 1 minute has 60 seconds. So W is equal to what? 200. 200 times 2 times pi divided by 60. I'm getting 20.9, I'll say roughly 21. I'm not typing my answer on the computer, so 21 is good enough. Rad per second. Next, I need to calculate the inertia. And to calculate the inertia, I'll go to my book, to that chart, and it says, if you have a beam, and the beam spins around its center, and that's what the blade is a beam that's going to spin around the center. The inertia for that is 112 ml squared. See that? I don't know if you can see it on the screen. Can you see that number? 112 ml squared. So let me use that. Inertia is 112 ml squared. So my inertia is going to be 112. Do we know what the mass of that? 1 kilogram. Do we know what the length of that blade is? 0.5 meters, and you got to square it. Uh, 0.5 squared divided by 12. My inertia is 0.021. So how much kinetic energy due to rotation does the system have? 1/2. What is I? I is 0.021. That's the inertia. What is W? 21, and don't forget to square it.
Question.
Yes.
Just to make sure the 1/12 is that specific formula, right?
Correct.
Okay.
For a beam that spins around the center.
So I'm guessing on the test we'll.
You'll have that chart. Yep.
And that's mass length squared.
Mass times the length of the beam squared, correct. If that beam spins around this edge, this end here, it will not be 112, it will be 1/3 ml squared. It's different based on that. So my kinetic energy due to rotation now is 4.6 joules. Remember, we did strings and springs before. We had a rope going over the pulley, and we neglected the pulley. Well, we're going to look at that pulley now and see what will happen. Before, we pretend like, oh, let's not even discuss it. Now, when we start to know about rotational kinetic energy, you can't really ignore it. I do it. Yeah, go ahead.
I'm sorry. Was
Yeah.
that 10.4?
The section 10.5, J. Yep. 10.4 is V equals R times W. That's what 10.4. We covered that last time, but it's not worth a section. Let's say you want to sharpen your blade for the lawnmower again. You bring it to, actually we have a machine upstairs that will do that for us. It's a grindstone. What it looks like a solid disc like this and spins around the center of it. It is solid. You take your blade and put it right next to it and it shaves it to make it sharp. So you got a grindstone right here. It's a solid shape. Let's say the radius of that, R, equals, that's a big one, 0.61 meters. That's a big radius, big stone actually. It's not a small one. That's massive. It's almost end to end more than a meter. It's about 4 feet, so it's like 2 feet radius. So we're not talking about a small stone here. Spins around the center right there. If the linear speed is V equals 1.5 meters per second, linear speed, and the stone rotational kinetic energy is 13 joules. Can you find I, the moment of inertia? So this stone sits on, I don't know, like a pedestal like this, piece of wood, sits like this. You bring in your, I don't know, axe, you want to sharpen it. You see the person holding the axe like this, try to sharpen against the stone there, and you rub it against that, and as it spins there, it sharpens that stone for you. Now, when you hold that axe there at the end of that, what's the distance from here to there? Isn't that 0.61 meter? That stone is actually from here to there, that distance is 0.61 meters. If you're holding on the inside of that somewhere, it's different, but you're holding at the edge of that. The question is, what is I? Well, the only equation that I know that has I in it so far is the kinetic energy. I left a space there intentionally again. I know Kr equals 1/2 I W squared. I'm giving you what the rotational kinetic energy, that's 13 here. I'm looking for I, but do I know what W is? I don't know what W. Can we find W? V equals what? Isn't that R times W? Do you know what V is? 1.5. Do we know what R is? 0.61. Can you get W? (1.5) divided by 0.61 equals 2.46. Now you know what W is. Can we find I now? How many unknowns you have there? One unknown. 13.0 equals 2.46 squared, then times 0.5, that's the half. We have 3.02 times I. And what's the inertia here equal to? 13 divided by that number. 4.30. Again, kilogram meter squared. MR squared. Kilogram meter squared. So inertia for that grindstone is 4.30 kilogram meter squared.